Climate change is potentially one of the greatest challenges we face as a species, and one of the largest contributors to this is travel. Globally, air travel contributes around 2% of carbon emissions every year. That's nearly 900 million tonnes of CO2 pumped into the atmosphere. With flying becoming more and more accessible, it's clear that these figures will continue to rise and risk damaging the environment irreparably.
The main issue with electrically powered vehicles is the energy density of even the best lithium-ion battery being limited to around 1 megajoule per kilogram, whilst gasoline offers a much higher density at around 43 megajoules per kilogram. This means that to power an aircraft by electricity alone will require a very large volume and mass of batteries.
To tackle this, we've designed a concept for an all-electric aircraft that uses highly efficient aerodynamics coupled with ultra-lightweight structural components in order to theoretically carry 10 passengers at a distance of 500 kilometres. That's roughly the distance between London and Dublin.
Trajectory optimization is a really key element in the design of an aircraft. Here we can see with much higher resolution the flight path and an energy estimate. It also ties everything together really nicely. It will tie together the structural and aerodynamic sides of the project. Through a combination of these, it will update and give you a visual graphical presentation of how the flight path changes with design changes.
The unconventional design uses a box wing structure to allow for greater lifting surface area, whilst reducing induced drag and a lifting fuselage that increases the total lift produced. The connector section between the two wings combats wingtip vortices, a phenomenon known to decrease aircraft efficiency, whilst the closed-loop nature of the wings reduces the total deflection of the tips.
Our aircraft incorporates a generative design-inspired isogrid fuselage. Our design can employ new technologies which have paved the way for bespoke filament winding techniques. We've tailored our design to effectively distribute the highest stresses from specific load paths in order to help us save weight.
The aerodynamic shape was designed and analysed using computational fluid dynamics to steer the result into the minimum drag configuration. Adjoint optimisation methods then refined this shape to increase the overall aerodynamic efficiency. CFD performance predictions were then validated using wind tunnel tests, verifying our claims and showing impressive aerodynamic capabilities.
The propulsion unit on this aircraft consists of propellers powered by electric motors. Power for electric motors can be generated entirely from renewable sources. Other advantages of electric motors are increased power to weight ratio, reduced operating costs, reduced maintenance, less noise and less pollution. Those factors combined make this propulsion system perfect for our aircraft.